Okay, so what I would say next, so as you saw, we went over example one, and that was going to take a while. And so what I would do next is I would say, okay, so now you try example two, but since we're running out of time, we'll skip that one. Well, I would have my students try this one on their own. I picked this one specifically because one of the zeros is zero, and that always kind of confuses them. And the other one is because sometimes they confuse with a complex conjugate of 5i. I'm not sure what to use. And so this is a nice way to extend what we've done. It's also easier the algebra, so they've seen a very tough one with me, and then now they can see one that's a little bit easier. And so I would have them do that. But because of time, what I would do next, maybe, or maybe I'd go over this one. I don't know. I'm not sure exactly how you want to do this one, but this one basically is the same thing as the last time. But what I like to is this last one. And so what happens is one of the things. Okay, and so then my transition would be as follows. I go, so far we've seen, one of the things I wanted to show you was here are some zeros of a polynomial, and how do you find the polynomial? So that's what we've been doing. We've been doing this now for a couple of sections, so now we want to ask the question the other way. Here's a polynomial, can you tell me the zeros? And so this actually seems like an impossible question in general. If you think about it, if I give you a polynomial of 100 degrees, how do you know there's a solution? And so this is why I consider this one of the biggest theorems in algebra. It turns out that if you have a function that's a polynomial of degree 1 or more, you can always find at least one root, 1, 0, and it can be complex, and it could be real, or I shouldn't say real or imaginary. Complex means it's going to be of the form a plus bi. That's all it means. And so the nice thing about this is if you have a polynomial p of x, if you can find a root, that means that somehow you can factor this into the following way. You can say x minus maybe the first root, a1, and then you'll have some other polynomial. Let's call it q of x. But if this polynomial here is of degree 1 or more, you can repeat the process, which means that you can actually factor, and let's call this q1 to say that it's the first one. You can do it again. You can say, so I have my first root, but if this q1 is a polynomial of degree 1 or higher, I could find a root of that one, and let's call it a2. And now I'll have a different root. Let's call it 2 of x. So the second piece right here comes from the q1. But, and you repeat this process over and over. What about this polynomial? If that one's a degree 1 or more, you keep doing this and doing this. And so what that means is that little by little, piece by piece, you can eventually factor out the polynomial. And the cool thing is here is that it turns out, and I want you to look at this theorem here, how many zeros are there? Well, if the polynomial has degree n, it has at most n different distinct roots, unique complex roots. So it could have up to n. It'll never have more than n. It could have less than n, and what that means is there might be some repeated roots, and we've seen that before in some of the work that we've done in previous sections. So there could be some repeated roots, but for sure at most it'd be n. And in fact, if you think of multiplicity, we'll talk about that later, but if you think of multiplicities, you can actually say it actually does have n. But we'll just say, we'll keep this word distinct to say that at most it'll have n. And so now this allows us to maybe look at example 3 and say, okay, well, this polynomial here is a degree 4, and I'm thinking at most it'll have 4 distinct zeros, complex zeros, 4 of them. And what they've done is they've actually given me a 0 right here, 1 minus I. And so the goal is to kind of find out the 0, and this is where all our work with synthetic division is going to be important, because that's how we're gonna solve this one. Is we're actually gonna solve this one by synthetic division. So let's go ahead and start this one. This one takes a while too, and so let's go ahead and see if you remember. The 1 minus I is a 0, so that's the piece I put in the box. The way I do this is the 1 minus I, and I put it in the box. And then the coefficients. The coefficient of x to the 4th is 1. The coefficient of x cubed is -7. The coefficient of x squared is 18. Sorry. The coefficient of x is -22. And then the constant coefficient is 12. Sorry, Melly. Hope that doesn't bother you. That's the train passing by if you can hear it. All right, and then of course synthetic division goes as follows. This first one always comes down, and then you multiply I wanted to use blue, sorry. So then you multiply 1 minus I times that, and so you get 1 minus I. And then when you do the math, negative 7 plus 1 is negative 6 minus I. I multiply negative 6 minus I and 1 minus I. I would do it on the side as scratch paper. I've already done it, so in the interest of time, I hope you believe me that this is negative 7 plus 5I. And so here we get 11 plus 5I. Okay. And then when you multiply 1 minus I times this, again, you can do it on the side of scratch paper. If I was teaching this, I would. But again, I don't want to make this video too long. So when you multiply these two, you get 16 minus 6I. And then when you combine these, you get negative 6 minus 6I. And then finally, when I multiply the negative 1 minus I, when I multiply the negative 1 minus I with the negative 6 minus 6I, I actually do get negative 12. And then this is my convention. I always put 0. I put like a little line to determine that this is what I'm done. And this is good. I want zeros. In fact, that's what's supposed to happen. It tells me that 1 minus I is a 0, so I should get 0 at the end. And so now here's where we use this idea of that these zeros come in pairs. And so if one of my 0 is 1 minus I, that means the other 0 is 1 plus I. And the beautiful thing about synthetic division is that I don't have to use the original coefficients anymore. Synthetic division kind of works really nicely in the sense that it'll lower kind of. I don't have to use these numbers. I could actually use these bottom ones because it kind of lowers the polynomial, and so I'm going to use those in my coefficients. So 1 minus 6 minus I, 11 plus 5I, minus 6 minus 6I. And so here is this. And so now, of course, you bring the first one down. So this is a 1. When you multiply, you get 1 plus I. Here you get, I wrote this down, you get negative 5 actually. And then when you multiply negative 5 times this, you get negative 5 minus 5I. And then when you do the math here, you get 6. Then 1 plus I is that, and you get 6 plus 6I. And then notice, yay, this is a 0, another 0, which is what we wanted. This is exactly what the theorem was saying. And so now you can connect it, and now I can connect it. You say, ha, here's a 0, it worked, yay. Here's a 0, it also worked, good. And not only does it work, though, this is again the beauty of the synthetic division and of understanding polynomials, is this p of x. Let me use black. This p of x, which we know is x to the 4th minus 7x cubed plus 18x squared minus 22x plus 12. When you factor this, since you have these two zeros, these ones in red, one of the factors is x minus a 1 minus I, because 1 minus I is a 0. So the idea here is that when you plug in 1 minus I for x, this 1 minus I you plug in for x should cancel the 1 minus I here. The other factor is x minus the other 0, which is 1 plus I. And again, the idea is that if you plug in the 1 plus I into the x right here, you should get 0. And the final thing is the fact that these coefficients that are here, the 1, the negative 5, and the 6, that gives you your other polynomial, x squared minus 5x plus 6. And again, if I was teaching this, I would say, oh, well, remember that this first 0 gives us our first factor. The second 0 gives us our second factor. And then complex, recall we've done this so many times, that these coefficients at the end give us the polynomial. And the nice thing is that we know how to factor. We really do. And so here what happens is that we get p of x is equal to x minus 1 minus I, x minus 1 plus I. And here you get x minus 2, x minus 3 just by factoring. And now we can answer the question. The question is, find all the complex zeros. Well, now we can look at this nice factored polynomial. In fact, on your homework, I'm sometimes going to ask you for the factored polynomial, not for the zeros, so you have to know both. But here from this, you can see that the zeros are x equals 1 minus I. That comes from this factor. This factor here tells you that x equals 1 plus I. And then what we know from before, this factor tells you that the other 0 is 2, and our last 0 is x equals 3. And so we found all those zeros, and this is how you connect it back and forth. And of course, if I was continuing this lesson, I would continue doing more examples. This might be a whole day. I would do more examples of this, give them a chance to try it on their own. And then we would talk about, well, can you always do this? Can you always factor it? And what are some theorems that help you kind of get started? And the big picture here is that, wow, this is kind of hard. This is kind of long. And in fact, it's not always guaranteed. It's not always possible to find these zeros. And so what we do then is we this is why calculus is invented. And so because calculus gives us a way to find zeros. And in fact, group theory was invented because it's not always possible to do something like this. But anyways, I hope that helps, and I'm going to go ahead and stop because it's already kind of a long video.